That's Saturn. Not the sound of wind, not the rings. That's electromagnetic radiation converted into audio by NASA's Cassini spacecraft. And it sounds like a warning. From Earth, Saturn looks beautiful. Those iconic rings, that pale golden glow. It's the jewel of the solar system. But here's what nobody tells you. If you went to Saturn, you wouldn't come back. Not because you chose to stay, because the laws of physics won't let you leave. The distance is too far, the fuel requirements are impossible, and by the time you arrived, your body would be so destroyed by radiation and microgravity that you couldn't survive the return journey even if you had the fuel. Saturn isn't just far away, it's a one-way trip, a death sentence wrapped in beautiful rings.
Let's start with how far Saturn actually is. 1.4 billion kilometers from Earth. That's not million, billion. Light from Saturn takes 80 minutes to reach us. If you sent a message saying, "I've arrived," it would take over an hour to reach Earth. The response, another hour back. Mars is 55 million kilometers away. We think of Mars as impossibly distant. Saturn is 25 times farther. A trip to Mars takes 6 to 9 months. A trip to Saturn, 6 to 7 years, one way. Think about that. 7 years in a metal tube. 7 years of recycling your own sweat and urine into drinking water. 7 years of cosmic radiation tearing through your body. 7 years watching Earth shrink to an invisible dot. And that's just getting there.
Here's where the math breaks down completely. To get to Saturn, you need fuel, a lot of it. But here's the problem. Every kilogram of fuel you bring needs more fuel to move it. And that fuel needs fuel. And that fuel needs fuel. It's called the rocket equation, and it's one of the most brutal laws in physics. NASA's Cassini probe took 7 years to reach Saturn, and it didn't fly straight there. It couldn't. There wasn't enough fuel. Instead, it looped through the solar system, swinging past Venus twice, Earth once, Jupiter once, stealing tiny bits of momentum from each planet's gravity just to build up enough speed. And Cassini was a small, unmanned probe. A human mission would need life support, food for years, water recycling, radiation shielding, medical equipment, spare parts. The mass becomes catastrophic. The more mass you try to move, the more fuel you need. The more fuel you need, the more mass you have. It's a death spiral with no escape. But let's say we solve that. Let's say some future technology gets us there. Now the real nightmare begins. In deep space, there's no protection, no magnetic field like Earth has, just you and the cosmic radiation. Astronauts on the International Space Station are shielded by Earth's magnetic field. They get about 150 millisieverts of radiation per year. That's manageable. On a trip to Saturn, you'd get 600 to 1,000 millisieverts per year. Over 7 years, that's 4,000 to 7,000 millisieverts total. NASA's career limit for astronauts is 1,000 millisieverts for their entire career. A single trip to Saturn would exceed that limit by 4 to 7 times. And there's no shielding that works. The particles are so energetic that thick armor actually makes it worse by creating secondary radiation when the particles slam into it. Your DNA would be shredded, cancer risk would skyrocket, your brain would literally deteriorate, memory loss, cognitive decline, decision-making impairment. By the time you reached Saturn, you'd already be dying. But radiation isn't the only thing destroying you. Astronauts on the ISS spend 6 months in microgravity. Even with 2 hours of exercise every day, they come back with bone loss and muscle atrophy. A Saturn mission means 7 years of weightlessness. Bones lose 1 to 2% of their density per month in zero gravity. After 7 years, you're looking at 80% bone loss.
Your skeleton would be so fragile that standing up, if you ever felt gravity again, would shatter your legs. Your heart would shrink, your muscles would waste away, your immune system would collapse, your vision would be permanently damaged. After 7 years, you wouldn't be human anymore. You'd be a fragile shell, barely capable of surviving in any gravity. And here's the worst part. You'd still have to make the return journey.
Let's say you somehow survived the trip to Saturn. Radiation damaged, bones like glass, but alive. Now you need to come home. To leave Saturn's orbit and head back to Earth, you need fuel. Massive amounts of fuel. But remember, you had to bring that fuel with you from the beginning, which means you needed even more fuel to carry that fuel. The rocket equation doesn't just apply to getting there, it applies to every stage. Slowing down at Saturn, speeding up to leave, slowing down at Earth. The fuel-to-payload ratio becomes so extreme that the mission would require either a spacecraft the size of a city or propulsion technology that doesn't exist. This isn't an engineering problem, it's a physics problem, and physics doesn't negotiate.
If you went to Saturn, you would die there. Not eventually, not possibly, definitely. And maybe that's okay. Maybe some frontiers are meant to stay untouched. Some jewels are meant to stay distant. Saturn will always be beautiful, and it will always be impossible.